Hello. My name is Judith Dawes. I'm a professor of physics at Macquarie University, and I would like to welcome you to the university. And we're all looking forward to hearing David Coutts' lecture. But I would like to start with an acknowledgement of country. Australia's story begins with the oldest continuing cultures on the planet. Across an incredible 70,000 years, Aboriginal and Torres Strait Islander peoples have forged knowledge as Australia's first scientists and engineers. This deep knowledge of country is embedded within songlines and safeguarded by culture, leadership, authority and law. We pay our respects to traditional owners across the country and to the traditional custodians of Macquarie University land, the Wallumattagal clan of the Darug Nation, whose customs and cultures have nurtured and continued this land. So welcome, and I would now like to introduce Dr. Graham Melville from the Australian Institute of Physics.
Thank you, Judith. Also welcome from me. It's great to see you all. Look, I can't barely see any spaces anywhere. That's very, very crowded. Thanks very much for coming along. It will be a very exciting night. Plenty of demonstrations, and it will be very enjoyable. So the Einstein Lecture is an annual public event by the New South Wales branch of the Australian Institute of Physics. This year will be the 18th Einstein Lecture, and we have very distinguished speakers over the years who will cover a wide range of topics with an emphasis on Einstein's ideas and their consequences for physics and technology today. The topics have ranged from quantum computing to plasma physics and to astrophysics. This lecture engages audiences with the wonders of physics, especially young people, and highlights the recent advances from world experts. The Australian Institute of Physics, AIP, is Australia's premier physics organisation and promotes the role of physics in research, education, industry and community. Now, the New South Wales branch is very active. We have a number of events like this one. We have Women in Physics, we have student prizes, we have Physics Industry Day, a whole lot of things. And also this Friday night, we have Physics in the Pub. So that will be a very exciting event as well. It's sort of a laid-back type physics. You've got to be over 18 years of age, though, to go to that one. Now, tonight's talk. It is an Einstein lecture, so there's got to be a connection between Einstein and lasers. In 1916, Einstein devised an improved fundamental statistical model of heat embracing quantum energy. His theory predicted as light passed through a substance, it could stimulate the emission of more light. This effect is at the heart of the modern laser. Now, Einstein didn't invent the laser, it was invented around 1960, but his work laid the foundation. And you can see today there are many aspects of lasers, CDs, DVDs, laser pointers, barcode scanners, a whole lot of them. Now, we're very lucky tonight for tonight's speaker, Professor David Coutts, who is the Deputy Dean of Research and Innovation in the Faculty of Science and Engineering here at Macquarie University. From 2016 to 2018, he was the Director of MQ Photonics Research Centre, and from 2009 to 2012, he was the Head of the Department of Physics and Astronomy. Professor Coutts is a member of the Optical Society of America and also the Australian Optical Society. He was previously at Macquarie University as a research fellow from 1992 to 1994. He then spent 8 years in the Department of Atomic and Laser Physics at the University of Oxford, first as a postdoc research associate, 1995 to 1999, and then as an AIP SRC Advanced Research Fellow from 1999 to 2003, before returning to Macquarie in 2003. His research interests involve applications of optics and lasers. He also likes to have fun with high-power laser, or who doesn't? Actually, I can remember the first time I got a laser. No, maybe I won't talk about that. Okay, so if we could give a very warm welcome to Professor David Coutts, who has the topic Lasers Making Light Work.
Thank you. Thank you very much. Well, thank you very much, Graham, for that very warm welcome. And I'm thrilled to be giving the lecture today, and I hope we'll be able to get some demonstrations to work. We're constrained by laser safety as to what we can do, and I've pushed the boundaries as far as I dare. So I'd like to dedicate today's lecture to the memory of Professor Jim Piper. It's a sad note to begin with, but Jim sadly passed away a few weeks ago. And Jim was enormously influential in laser physics and in research in Australia and at Macquarie University. He was a mentor to a great many people, a PhD supervisor to people still with us in the university today, including myself. So he will be very, very sadly missed. He's an extraordinary leader and mentor. And some of the elements from today's talk, actually, I first heard in a public lecture that Jim Piper gave, I think, in this very room 30 years or so ago. So laser physics the basics of lasers hasn't changed much. So I begin with what is a laser. It's an acronym for light amplification by stimulated emission of radiation, which is a bit of a mouthful, and it's as Graham alluded to, this is something that, it's a process that was first predicted by Einstein when he was considering the way light can interact with atoms. So if we look at this, imagine we have an atom that can have two energy states, a low energy state and a higher energy state. So E1's the low energy state, E2's the higher energy state. That atom, if it's initially in the low energy state, indicated by the green dot, and then a photon of light, a particle of light, can come in and be absorbed by that atom, and it transitions up into the high energy state by absorbing a photon of light. And that process is what gives you the colour of the clothes we wear, for example, is the absorbing different colours of light. This is the amount of absorption depends on how many atoms you have that are in state E1. So another possible process is our atom that's in the high energy state can decide to spontaneously jump down to the low energy state and give up its excess energy as a photon of light. And this is an inherently random process. And this is what causes, yes, we do have fluorescent light bulbs in this room, and it's the light you're seeing from those fluorescent light bulbs, is that exact process. What Einstein realized, though, is that this process, there can be a third form of interaction, which he called stimulated emission. And this is when you have an atom initially in the high energy state, and a photon of just the right frequency comes in and it stimulates that atom to release a second photon and transition to the low energy state. So we now have two photons, and those two photons are completely indistinguishable. And this is the special property that we harness in making a laser work. So it's not something that was obvious to predict, and it took someone of Einstein's genius to understand the physics behind this, how this would occur. So the rate of stimulated emission depends on how many atoms are in state E2, the higher energy state. So real atoms don't just have two energy levels, they usually will have multiple energy levels. And we can have transitions or jumps between different energy levels. For example, we can have a jump between those two energy levels. The difference in energy is not very much. And so that'll emit a low energy photon, which will be characterized by red light, for example. Jump between a larger separation in energy levels could emit a green photon of light, and we could get a blue photon of light emitted. So real atoms have multiple energies, and they will produce a more complex spectrum. Such as we see here, for example, is an example of spectra you might get from different discharge lamps. Every atom will produce its own characteristic spectrum, a spectral fingerprint. The challenge for getting lasers to work, though, is all of those three processes I talked about occur at the same time in a real system. An ordinary state of matter, most atoms will be in their lowest energy state. And I've indicated the number of atoms in each state by the length of the horizontal bar. So most atoms are in their low energy state, and as you go up the ladder, there's fewer and fewer atoms. What this means is between any two levels, you're more likely to have absorption than you are to have the stimulated emission process occurring. So that won't operate as a laser. So this is why you're not getting laser beams shooting out of the fluorescent lights up here at the moment. What we need to do is we need to create a very special situation where we have a difference in energy. And this is what we call a population inversion, where there's more atoms in the upper level of a laser than there is in the lower level of the laser. So we need some kind of pumping mechanism to drive atoms to be in that upper state. If we do that, we can have the situation where the stimulated emission dominates, and we can potentially produce a laser from that. If we have a process like spontaneous emission that clears out the lower of those two levels, the E1, and keeps its population down, the number of atoms in that state low enough, and that could be spontaneous emission, for example, then we can keep this process going indefinitely and produce what we call a continuous wave laser, a laser that's producing light as a constant stream of light. So if we get this pumping mechanism right, we can get stimulated emission to dominate and potentially build a laser. So there's lots of different ways we can pump lasers to get this population inversion, because it's not something that is found in nature very often. So we can absorb light or photons from another light source, and that light source could be, for example, a flash lamp, like a camera flash. Could be another laser, which is very commonly done, or it could even be sunlight. You can have solar-powered lasers directly pumped with sunlight. Another common method is to use an electrical discharge. This is where in a discharge you have electrons colliding with the atoms, and that knocks them into the upper laser level. This is a very common process inside gas lasers. Other possibilities include things like chemical reactions, where you react chemicals together and the product of the chemical reaction is atoms or molecules in this excited high energy state, and then they can release that energy as a laser. There's even been proposed to use nuclear explosions, but that's not been done for a very long time and is not recommended. But it has been said that if you hit anything hard enough the right way, you can potentially make it laze. So what are some of the different types of lasers that we see? So gas lasers are one of the common early types of lasers, and these operate with an electrical discharge. And so I have one example of that, which is a helium neon laser. And this is, if I take the lid off this laser, you can see a glowing discharge from helium and neon atoms in a tube. They're glowing away. So that's a type of gas laser. We can make liquid lasers using liquid dyes, and I've got some liquid dyes set up here which are glowing away quietly, and if I dim the lights you'll see that a bit more clearly. Different dye molecules dissolved in a solvent will glow different colours, and we can create our laser using that process. We also have lasers made out of crystals. We have semiconductor lasers, which are your laser pointers, and we can have lasers made out of crystals, and you probably can't see this very easily, but this is a crystal of alexandrite, which is a very rare and very beautiful gemstone. It's very expensive. This is a synthetic crystal. Most jewelers sneer at synthetic crystals. Laser physicists want the synthetic crystals because they're nice and pure. So this can make an infrared laser. And this one I don't think glows as well, but this is a pink sapphire crystal. So we can make lasers out of sapphires, emeralds, rubies, garnets, all different sorts of solid crystals, and there's just a sample of them shown in the picture there. So we've talked about this stimulated emission process, but that's only half the story with making a laser. What that means is we can produce optical amplification. One photon can stimulate the emission of 2 photons, so that we've got 2 photons go on to make 4 photons, go on to make 8 photons, and so on. So this is an optical amplifier. And what we want to do is to work out how we can turn that into a laser. So a high power amplifier will produce a hiss. That's what you get from an audio amplifier. If we have a small input signal, the amplifier will amplify that input signal. To make a laser, what we want to do is make an oscillator where we take a little bit of that output and feed it back into the input. And then this will turn an amplifier into an oscillator. Now, you've all heard this before, and one way of doing this is with an amplifier, an audio amplifier. And the owner of this is left, so I'm not sure if I can get it to work. Just turn the mic on. So here's, if I put a small signal in, it's being amplified there. If I take some of the hiss coming from this thing and feed it back in, sorry for those who are auditory sensitive. So what is happening here is the amplifier, because it's getting feedback, it's screaming at you. We do exactly the same thing optically. So a laser is like an optical amplifier with some feedback, and it's screaming at you, but it's screaming at you with light. So how do we do that in practice? So we have some laser medium, which could be, for example, a rod like this one. This is from a laser. And we pump it somehow, which could be by wrapping a flash lamp around it, so it's now becomes a gain medium and amplifies. And then what we do is we'll have in that medium, we'll have some spontaneous emissions, say the arrow in yellow on the left-hand side. And as it propagates through the amplifier, it gets amplified. If we then put a partially reflecting mirror at one end, it'll reflect some of that light back, which will get further amplified. And if we put a mirror, fully reflecting mirror on the left-hand side, we can bounce back and forth between those 2 mirrors. And if we do that, we can get a laser to operate. So we take our rod and our flash lamp, and we put it between 2 mirrors. One is 100% and one is a partially reflecting mirror like this. Okay, and if you get all those elements just right, you can create a laser. Those are the essential elements we need: the gain and the optical system that makes it what we call an optical resonator. It resonates the light between 2 mirrors. And because the light is bounced back and forth thousands of times, it is a very directional beam. So what we're working with is light oscillators by stimulated emission of radiation. But the astute in you can work out why we don't call them that, why we don't want to work with those things. We prefer to call it lasers. So the very first laser was a miniature version of that thing I just held up, where the laser rod was a ruby rod, a synthetic crystal of ruby, literally with a flash lamp wrapped around it, and the mirrors were coated as coatings on either end of the laser rod. So this was made by Ted Mayman in 1960. There's a picture of him holding it up, so it was a very small little device, and it was started off the revolution in lasers. And it's amazing that lasers exactly of that configuration were fairly soon thereafter sold as products in the market. So I've just done that demo. So let's look at some of the characteristics of lasers. and what distinguishes laser light from torchlight. So we're very used to a torch producing white light going in almost all directions, but we put some mirrors around it to point it roughly in one direction. So I have a demo of a torch here, which I'll just shine it onto a grating and I'll try and dim my lights if I can. And so we can see there we have a nice spectrum of light. So this torch is producing all the colours of the rainbow. So laser light is very different from that. But the next step is to just consider, if I unmute my projector, if we just consider a lamp, like a discharge lamp, which has got atoms in it, and those atoms will only emit certain colours of light where the colour is determined by the energy difference in the different energy levels inside that atom. So if I turn my torch off and slide my grating across and mute the screen, hopefully we can see. You can see on here, it's a little bit hard to see, the doors open. We've got some different discrete colours. So I'm separating the light from a lamp into its different wavelength components, the different colours. And there's red, yellow, green, greeny blue, all the way through to blue. Particular wavelengths of light only. But being it's still what we call an incoherent source. The photons are going off in every which what direction. This is what's happening, as I said earlier, in the fluorescent light bulb of ours when it's turned on. So a laser, by contrast, and I've got a little laser, I'll shine it off the same grating to separate it into its colours. If I can do that carefully. And we can see, in contrast to the torch, turn the right thing on. In contrast to the torch, it's producing just a single colour, and it's just one little dot of light here, rather than a big smear of light. So unlike a torch, a laser beam, because that light has had to bounce back and forth thousands of times between the two mirrors inside the laser, it produces what we call a coherent laser beam. And that coherent beam is incredibly useful. It's what really distinguishes lasers from other light sources. So what does that mean? So let's look at some examples of lasers now, different ones, and the ones that you're probably quite familiar with are laser pointers, because you can buy them for a few dollars. Be careful buying them on eBay, because they're often not very safe. And my trusty assistant is going to help, Helen Pask, as we demonstrate, and I'll turn the light out and we'll try and demonstrate some laser beams in the room, because why not, it's fun. So I've got 3 different colours of laser pointer here. I've got a red one, a blue one, and a green one. And it's hard to see these laser beams because, and if I dim my screen, it'll be easier to see, but if the laser really only scatters off the air or the dust in there, and we need some dust. So Helen's going to shake out the, that's more pretty. So this shows you, some of the great characteristics of these lasers. They're incredibly useful, not just for pointing and fun and lecture rooms and the like, but also you can use them as a straight line for surveying, for example. There's a myriad of uses just for little tiny lasers like that one that cost a few dollars. Another type of laser is the one I was showing you earlier, which is a helium neon laser. Now in a helium neon laser, and I've got another tube of one here, We have an electrical discharge tube with a couple of mirrors coated on each end, and we put an electric current through this, and you saw it glowing before. I'll turn it on and try not to blind anyone with this low power helium neon laser. I've got to be a little bit careful where I point it, so I'll point it up at the ceiling. So you can see it's giving that little red dot on the wall. So very, very simple device. It's got a mirror at each end and an electrical discharge and a gas of helium and neon. And these produce a very beautiful little beam on it, which spreads out only very slowly. It's a small dot here and it's a small dot on the wall. So that's a type of gas laser. There's many, many gas lasers, including ones that are 1,000,000 times more powerful than that, and I can't show that in this lecture theatre, unfortunately, for safety reasons. Another type of laser that is quite a pretty laser is the dye laser. I'm showing these dyes glowing away here. We can use those to make a laser, and what we've got to do is we've got to get light in, and we've got to put some mirrors around. And you can see in that picture a green beam coming in. It's pumping, putting energy into a liquid dye solution, which is the glowing yellow, and there's a red laser beam coming out of that. I'll show you what this looks like. Dyes are quite different from the atoms I was showing you earlier. They're much more complicated molecules, and so the energy levels are much more complicated than that simple structure, simple ladder I showed before. Effectively, the energy levels are divided up into bands. It's like we have a lower group of energy levels and an upper group of energy levels, and there's thousands and thousands, and they're all smeared out. And that's because it's a very complicated molecule interacting with a liquid. What that means is that this laser can produce photons of a whole range of different colours, depending on the initial and final state. So with these things, you can make a tunable laser. So how does that work? So we have a liquid dye flowing in a glass cell, which is indicated in that orange parallelogram there. We shine some green light in it from another laser, a more powerful one of the version I was just holding up. And then we put a prism in the cavity to choose which colour will go back and forth between these two mirrors. This is a fully reflecting mirror, and the right-hand one reflects some of the light and lets some of it out as the laser beam. And by changing the angle of this mirror, we can change which colour bounces back and forth thousands of times between those two mirrors. So by rotating this end mirror, we can tune the wavelength or the colour of light that the dye laser produces. So this is one of the very powerful aspects of laser, is that they can be tuned very precisely, so you can get exact frequencies you want. For example, if you wanted to interact with particular atoms only, you can tune your laser in to just hit the absorption features of particular atoms. But dye lasers can be much simpler than that. This piece of plastic I have here is also a type of laser. The front and back surface of this perspex has some reflectivity, so you can actually get lasing bouncing back and forth between the front and back surface of this. If you put it in a powerful green laser beam, more powerful than this one that makes it glow a little bit. If I use a pulsed laser, and I did this in my lab, you'll see on the screen here a yellow dot moving around as I literally wave this very piece of plastic in front of a green laser beam. The simplest kind of laser you can imagine, just a piece of plastic. As I said earlier, if you hit anything hard enough, sometimes you can get it to laze. Another popular type of laser is a titanium sapphire laser. So we're looking at something that's slightly more complicated here. Rather than just having two mirrors, we've got 4 mirrors. These 4 mirrors is just really to provide a bit of additional control over the laser. We have a sapphire crystal in the middle. It's a pink sapphire. It's got extra titanium in it, which gives it the pink colour. We come in with a green beam that pumps up to the upper laser level, and then we get lasing across these 4 mirrors back and forth, and this mirror lets some of the beam out as our output beam. And again, by putting a tuning prism inside this cavity, we can choose the wavelength that comes out of the titanium sapphire laser. And that overlay is a picture that I took of one of the lasers from my laboratory. It's an infrared laser, so you can't see, so I've used infrared film, so the green looks blue and the infrared looks red using infrared film. But you can see literally that beam bouncing around inside, and a little bit of it comes out this mirror as the laser output. So this shows the sort of things we can do with lasers. We can put extra optical elements inside the laser cavity, inside that resonator, to choose exactly and control exactly what the laser does. So a lot of laser physics and laser engineering is manipulating these optics to get the laser to do exactly what we want it to do. Sapphire is a laser that you can manipulate in so many different ways. You can run these lasers where they're continuous, the output is coming all the time, like in my laser pointer, all the way through to producing the shortest pulses ever we can produce, a few million billionths of a second long. Crazy short pulses can be produced from these lasers. So what are some of the characteristics of lasers? They can be high power, up to many thousands of watts. Tens or hundreds of thousands of watts you can buy now from commercial suppliers. This is millions of times more powerful than my laser pointer. It's very scary. They can be highly monochromatic. If you control that resonance exactly right, you can get frequencies that are accurate in about 1 part in 10 quadrillion, if I've got my definitions right, about 1 part in 10 to the 16. Frequencies that are stable to an unbelievable level, and these are the sort of things that interact with atomic clocks and our best precision that we can do in terms of timing. You've already seen that lasers can be highly directional, which is why they're great for laser pointers. They can be pulsed, as I said a minute ago, so we can store lots of energy in a laser medium like this rod and release it all in one really short pulse that lasts maybe a few billionths of a second long. So this is a way of getting incredibly high powers for a very, very short period of time. And you can store lots of energy in a system like this, which is again what gives lasers some of their amazing characteristics. So we can potentially put lots of power or energy focused down with a lens because it's such a directional beam. We can focus it down to a tiny point and put an incredible amount of power or energy into that tiny volume. And as an example of this is one of my lasers focused just in air. That laser had a pulse duration of about 50 billionths of a second, so 50 nanoseconds, a few millijoules of energy, but during that pulse it was producing 200 kilowatts of power, but just for a very short period of time. And it was doing that about 6,000 times a second, and that was enough to actually tear apart the molecules in the air and create a stable spark, which is what that little blue spark in the middle is. So you can actually get lasers to break down air. Now that presents one of the problems of lasers, because if they can do that to air, what might they be able to do to our eye? Key characteristics of lasers, they can be focused to a very small point. So even a low power laser pointer can be focused by your eyeball to a tiny dot on the retina and damage it permanently. Is why laser safety is a real issue, and it's a constraint on what I can do in this lecture today, because I don't want to permanently blind anyone with a laser. So when using lasers, you should always use the appropriate safety gear, put on laser safety glasses. But let's take that idea to the most extreme. One of the largest lasers in the world is the National Ignition Facility in the Lawrence Livermore Laboratory in the United States. It's a laser the size of a building. You can see in the bottom there some cars. There's a whole building that's filled up with lasers. Very similar to these rods, but on a giant scale, with giant flash lamps and huge capacitors. And what's the idea? is we're focusing 192 laser beams into this little target here, and in the middle of that target is a little pellet of deuterium and tritium. And the idea is to compress that pellet till it's about 100 times the density of lead, an incredibly high temperature, and the deuterium and tritium fuse together in a nuclear fusion reaction. And the idea is to get that to detonate with a small explosion. This has been done just in the last month or two for the second time, where we've got, in Livermore, they've got about 1.5 times as much energy out from the system as they put into it. So laser fusion for power is really challenging. This approach is a huge building. You need 150 times more electrical energy to drive the laser than you get out from this little tiny explosion. And this laser, at best, can fire once a day or so. At the moment, we've had 2 of these little detonations in the last 6 months or so. And to make power that's going to solve our CO2 issue, you'd need to be doing that about 15 times a second. So this technology is really a very, very long way away from actually producing the fusion power. But it's just an amazing system. What else can we do with lasers? Laser shows are fantastic. We all love what they look like in the night sky, and there's a company based in Sydney that does this sort of installation all around the world. This is one they did in Hong Kong, laser vision. It's just so cool. I like it. So I like the coloured lights. But one of the things with lasers is it's all very well shining them up in the sky, but when you've got a laser here and you want to use it in a factory over there, how do you get the light from the laser to where you want to use it safely? And to do that, we use fibre optics. So just as in electricity, you don't want to have exposed wires because that's super dangerous. We don't want to have exposed laser beams. We want to try and get the laser to go down this optical fibre. So I'm going to do a little bit of a diversion talking about optical fibres and how they work. And this is based on the idea of total internal reflection. So just to start with, imagine we've got air and water, for example, and we're shining a ray of light, a beam from a laser pointer into the water. You'll all know it refracts according to Snell's law, that bends the light downwards, and you've got to worry about that if you're trying to spot fish or spear fish, for example. And then we also get a little bit of light reflected. And depending on the angle that we send the light in, we get an angle of reflection equals angle of incidence, and we get some refracted ray. What becomes interesting is if you start off with light in the water, in the high refractive index medium, a medium where the speed of light is less in that medium than it is in the air, you get the same thing. You get a refracted ray and a reflected ray, still obeying Snell's law. I've just swapped N1 and N2 around in these diagrams. But what gets really interesting is if you go beyond this critical angle and the refracted ray, remember going into the water, it would bend down, or here's just the reverse. But the refracted ray, if you make this angle larger, it's got nowhere to go. And what happens then is you get total internal reflection. So the light will reflect with 100% efficiency in theory. And if the angle's larger, we can keep doing that. So this is the basis of making an optical fibre. We have a glass rod that's got 2 different types of silica glass. The inner one has got a slightly higher refractive index than the outer one, so it's shown in cross-section on the bottom here. And we launch a ray of light in the end, and it bounces up and down by total internal reflection. And it can do that over 100 kilometres of length if you make the glass pure enough. So this is how we make optical fibres. They're incredibly useful and incredibly powerful. And I'm going to attempt to demonstrate that total internal reflection because it's kind of fun. And so I'm just going to see if I can get, that's the right camera. And I will dim the lights. Mute our projector. No, I'm not going to mute the projector because then we can't see what we're doing. Let's try and see if I can demonstrate this because what I'm doing here is I'm shining a laser beam into some water that's got a little bit of dye in it that makes it glow, and there's a reflection between the water and the perspex, and you can see that beam is bouncing up and down as I do this. So that's effectively how we can make an optical fibre. Now I love fibres because they're cool, and we can, good, we're back again. We can, we'll demonstrate one in a little minute, but I'll just go through a couple of the things we do with fibres. So fibres allow you to get light from point A to point B along a flexible little rod of glass. It's a fibre of glass that is only about the size of a human hair. And we can launch light in of lots of different colours down the same fibre, and we can separate the input with a prism and the output with a prism or the equivalent. And we can send pulses of light representing data down that fibre. And because lasers can produce such incredibly short pulses, we can send a crazy number of pulses per second through this one optical fibre. An enormous number of bits per second are possible. So just compare that with copper wire as a cable. This is the sort of cable that you used to have, and we still do, unfortunately, going to our homes, which maybe that bundle could handle 50 calls. An optical fibre can handle maybe a million phone calls. This is what the world used to look like before NBN on long-distance cabling. That bundle of wires to transmit phone calls that can all be handled by a single optical fibre now. This is what's really revolutionised communications. So in addition to the NBN fibres around Australia, there's a global network of undersea fibre cables that is what allows us to access the internet without even thinking, where is the data coming from? Which country is it coming from? We don't even know. So Australia is well served, but there's enormous cables going all around the world. Now here at Macquarie University, Professor Mick Whitford and Simon Gross have been part of an international collaboration who've recently demonstrated a world record of sending data through what is becoming more of a standard optical fibre. So this is a fibre that's an eighth of a millimetre in diameter. It's got 9 of these core regions where the light travels. So rather than just one, it's got 9 of them to get 19 times as much data. And they've demonstrated 1.7 petabits. That's about 17 million full-speed NBN links through a single optical fibre, which is just phenomenal work. And this is a global partnership involving Australia, Japan, and the Netherlands. But we can also use fibres just to get power from A to B. For example, lasers can be used in many industrial processes with high power lasers. So this is a fibre spool that's got about 10 watts going through it over a few metres. And I'm hoping, if everything works well, I can demonstrate that for you, because it is kind of cool. So wish me luck here as I turn this laser on. Starting to go. All right. Let's turn some lights out and we'll just see if we can really get that to hum. So this is about 2 watts of light. I'm going to crank it right up and hope we don't burn anything. Oops. So I might set fire to something if I'm not careful. So this is a visible laser. Most of the light is actually going from one end of the fibre to the other, and a little bit of it comes out the side, which is just loss. And that's because fibres scatter a relatively large amount in the visible compared to the infrared. Same reason the sky is blue, it scatters blue light more than red light. So we don't use green lasers for telecommunications where we want to send fibres for hundreds of kilometres. We use infrared lasers where the fibres have very little scattering and very little absorption. But you can't see infrared. This is much cooler because it's green. And I have to take particular precautions when doing this, including setting it up so that if the fibre breaks, the laser automatically turns off. So what do we do that for? In many cases, we want to use lasers to send power from A to B, and it's a very convenient approach to do it in a safe way. Obviously, I had bare cable there. You would put the cable in a special metal tube so that no one stomps on it and breaks it, for example. So you can actually make lasers out of fibres as well, where the actual medium itself is the glass fibre. And you can buy these at a scary low price for about $10,000 on Alibaba, no adverts. You can buy one of these things from China that produces 1,500 watts of power. So that's about 1.5 million times what you're legally allowed to have as a laser pointer. And it's scary to look at people on the internet who are using these lasers without glasses on to do laser welding and the like. And so that laser is hot enough to melt and weld steel, which is quite amazing at low cost. Please think very carefully before you go out and buy one of these things. They're quite scary. In fact, high-power lasers have alarmingly entered the consumer market. So again, for not much money, you can go out and buy yourself a laser engraver with a 5-watt laser in it, or a 40-watt laser perspex cutter for cutting up plastic like this. They've got some very scary lasers in them. And so if you do have one of those or access to one of those, please be sure to follow all of the safety directions when using that equipment. They should be designed, the one on the right, that no laser light can come out and it won't turn on unless the lid's closed, but the one on the left, if you were silly enough to put your watch underneath the laser engraver head, you would get a laser beam in the eye. That is really crazy. So be careful, because these are common. Many schools have them, for example, in their workshops. So lasers are enough to heat and melt and evaporate metal, and so one of the natural things people are doing with them increasingly is using them in metal 3D printers. So the laser melts a powder of metal or a wire of metal and builds up structures. And people are taking this to extremes. So Relativity Space are 3D printing entire rockets and rocket engines. So it's good for rapid prototyping, but also people are thinking about using this increasingly in production. So you can possibly see on the right-hand side a ladder and a chair. This is a big rocket tank. One that I saw just recently in the media, which was amusing me, is using lasers to do weeding. So here you have a robot tractor driving over the seedlings. It has a scanner to work out and an image processing system to determine which is a weed and which isn't, and then it fires a laser to zap the weed and kill the weed. Pretty cool, actually. That's not faked, so you can go and buy one of these things. So it just shows you the sort of power of what's happening in this space. But to do these kind of interesting things, again, there's some very scary lasers involved in there, so just be careful. Another one that was in the news just a couple of weeks ago I saw is laser marking of avocados, so that you don't have to put the plastic stickers on them that don't break down in the compost. But it turns out that actually Marks and Spencers have been doing this in the UK since 2014, so it's a fairly well-known technique of laser marking fruit. And laser marking is used everywhere. The keyboard on your computer, the keys were written using lasers and things like that. Okay, so that's some of the sort of practical industry applications. I just want to talk about a few scientific applications. One of them is in laser velocimetry, where you're measuring the flow of a fluid using a laser. So the laser's acting like a stroboscopic flash. And because laser beams are so nice and well behaved, you can set up your laser beam to be a sheet of light and just illuminate one plane of a flow of fluid and seed it with some particles like Helen was doing earlier with the talcum powder. And your laser can be a really short pulse, so that even if the flow is supersonic flow, a particle will only move a micron or two during the exposure of the laser. So you can use this to freeze motion. And we've done that sort of thing. So here's an example of some particles in a flow cell, illuminated with a multicolour laser. I won't go into the detail there. And we've used 2 laser pulses, so each particle shows up twice. And that has, if you know the time interval between the 2 flashes, and you measure the distance, you can then work out the velocity of the particles, and you assume that is the velocity of the fluid that the particles are in. So this is a very powerful technique for mapping out fluid flow. If you expose the laser for longer, you can get some lovely fluid streaks in this, and this is a sort of a multicolour thing I was doing a few years ago. It's just so pretty, but I can't show it in here quite like that. But I can show something a little bit similar. This is using a blue laser. I'll just put that in the background and we'll see if we can turn that on, because I've got that set up here. I hope. So this is a blue laser that's actually from a laser engraver, and it produces a nice blue beam. And if I dim the room lights, and maybe I'll mute my projector as well, hopefully you can get a little bit of a sense of what's going on. I'm going to try lighting a match so you can see some smoke from a match, because it looks pretty. That's pretty. So if you were replaced with a camera and you took some fast photography of that, obviously you can see an analysis of the fluid motion just within that plane. And here's just some water spray, if I get that right. There's quite a lot of air blowing around in this room, which is making it look... But you can see beautiful turbulent motion in the air. I think it's so beautiful. And blue laser is a nice one, because blue light is scattered more efficiently by particles, and because blue lasers are relatively cheap. So this is a very powerful technique that is widely used in analysis of fluid flows, including, for example, understanding fluid flow inside an internal combustion engine by having special engines that have windows in them to let you actually look inside the engine. So another really important scientific application of lasers, taking us back to Einstein, we mustn't forget Einstein, is detecting of gravitational waves. So Einstein's general theory of relativity predicts the existence of gravitational waves. This is distortions in space. Space-time stretching and squeezing, and they arise from the movement of large masses, and the biggest masses around that can move fast are black holes. And this is a simulation showing 2 black holes in a death spiral orbiting towards each other. And as they do that, there's a lot of mass moving very fast. And according to Einstein's general relativity, that causes ripples in space-time. And those ripples propagate out away in 3 dimensions of space over enormous distances. And we now have instruments that can detect these waves radiating out from the merging of black holes or black holes and neutron stars, the most energetic things we know about in terms of gravity in the universe. So how do we do that? We use a device which is basically a souped up Michelson interferometer. So an interferometer, you take a laser beam, you split it into two beams with a 50% beam splitting mirror. One beam goes up and back down again, the other one goes across and back down, and then they recombine onto a detector. And because the laser beam is like a perfect sine wave of light, these two returning beams can either interfere constructively to make a bigger wave, or they can cancel each other out, the same as ocean waves can cancel each other out or reinforce each other. So this is a very sensitive tool to measuring the distance between one arm versus the other arm, the relative separation between these two arms of the interferometer. And a device like that is sensitive to a few nanometers, which is not remotely enough to detect gravitational waves. So how do you turn this into a gravitational wave interferometer like the LIGO one? And there's about 3 of these operating in the world. First thing you do is you make the arms enormously long so you can measure stretch over a very long distance. If you've stretched a rubber band and you want to know how much it's stretched by, have a really long rubber band because it's easier than having a really short one. They have test masses that are suspended on enormously elaborate pendulum systems because you don't want to measure the distance changing because of seismic effects, little earthquakes or cars or cows walking over the system. You put these all inside a vacuum chamber so there's no air effects. You add another set of masses here to make the light bounce back and forth just as it does inside a laser, and you can enhance the light. And while we're doing that, we might as well put another pair of mirrors to enhance the light even more. So bouncing back between these two mirrors, you may have 100 kilowatts of laser power, enormous amount of power. As much as you dare put in before the heat of the tiny, tiny, tiny amount of absorption on the surface of these mirrors distorts what's going on too much. And if you do that and you're lucky, then you can get a sensitivity such that when a gravitational wave comes past, the separation between this pair of mirrors and that pair of mirrors changes by 1/10,000th of the diameter of a proton in an atom. This is completely insane stuff to me, but it can be done. That's what people are doing now. And they have this kind of sensitivity to detect gravitational waves from these really energetic events like the merger of two black holes. This is one of the most exciting discoveries in recent science, and it's now becoming more of a tool to do astronomy. And at the heart of it is both Einstein's general relativity and an understanding and application of laser physics to an absolute extreme. It's astonishing that this can be done. This is teams of thousands of people have been working on this for many, many decades, and the breakthrough is quite astonishing. I have a demonstration, not of one of these because it's quite hard to do, but I have a little a lower power version of a simple Michelson interferometer. So if I turn my light off, turn my projector off, and turn the right laser on. If I can find the light switch. So on the screen here I have a little Michelson interferometer without all those extra bits and pieces I said. So the first diagram, a laser, a beam splitter, 2 mirrors, and the beam comes through up onto the screen. And in the middle of the screen, there's a dark thing because the 2 beams are cancelling each other out. But if I so much as touch this thing, just lightly touch it, or breathe on it, it is sensitive to that. It's incredibly sensitive to the tiniest amount of motion. But that is not remotely enough. That's why you have to go to these incredibly elaborate systems. But at the heart, this little instrument is what's allowing us to detect gravitational waves if you add on an enormous amount of very, very clever technologies. But in the form it is just here, it provides a useful means of measuring distances, for example, for controlling the positioning of a computer numeric controlled milling machine. So there's companies that sell kind of off-the-shelf devices that allow you to do this kind of measurement precision is the tiny distortion of the aluminium plate. When I just lightly rest my finger on it, you can see is immediately showing up there. So this kind of interferometer has practical applications as well as is very important scientifically. Okay, so the last thing I want to cover, because I know I'm running out of time well and truly, is, or the last couple of things, is we can use lasers for sensing, and you may have seen the ChemCam system on the Mars Curiosity rover. Fire a pulse of laser at a rock, look at the spectrum of the little bright flash of light that comes off, and you're analysing that spectrum, you can determine what the rocks are made of. So this is a type of laser remote sensing. Fire a laser at something, and by looking at what comes back, you can determine something about the object it was scattering off. For example, the coastal waters of Australia, we know the depth of them based on firing a laser from an aeroplane that flies over the coastal water, and just timing the time of flight of a pulse of light from the aeroplane to the surface of the water and to the bottom of the water where it reflects. So we have a team in the MQ Photonics Research Centre here at Macquarie who are doing just this, but to do a much broader range of measurements in oceanography. So Helen Pass, Dave Spence and team are sending a laser pulse into water, and they're looking at a whole range of effects of light that comes back. Light that comes back from the water itself, from phytoplankton, fish, so that's like the scatter you were seeing in this room from the blue laser. Fluorescence, so things that glow in the water, like planktons and the like. And then there's another type of process called Raman, which is a kind of nonlinear process. It's where the photon scatters off something and gives up a little bit of its energy to a molecule, and it comes back at a slightly different colour. And by analysing the spectrum of the light that comes back, you can potentially measure a whole lot of different things about the water. So you look at the input pulse, you analyse the time of that pulse as it comes back, and look at the different colours of the pulse, and knowing the time and the wavelengths, you can work out what's happening as a function of distance from the laser. So here's the team on a boat with the laser system, shining it into the water. So there's the complex laser system, and it's sitting in the corner of the room there. You can peer in as you leave. So this is designed to go on a boat and measure things like temperature and salinity and a whole lot of parameters of the water. So it's a very powerful technique. We use similar techniques for measuring everything from ozone layer thickness to pollutants from an industry, from a smokestack. Okay, the last thing I want to talk about is laser guide stars for astronomy. So this is solving a problem that has beleaguered astronomers since the first telescopes. So we have a star that sends starlight towards the Earth, and it travels for however many light years to get to Earth, and it produces almost perfect wavefront, perfectly in step photons. And then it hits our turbulent atmosphere, which messes it up. Now this is what makes the stars twinkle, which is all very romantic, but it is hated by astronomers because it messes up the image of the star, because it's like peering through, you all looked through the haze of a shimmer on a hot day, so that's what our atmosphere effectively does to the images. So there's a technique called adaptive optics in astronomy. So you take the light from, the starlight from a telescope that's got this messed up wavefront, and you reflect it off a special mirror that's got the reverse shape on the wavefront, so that when it's reflected off, it's perfectly flat again. That only works if you can actually measure what the wavefront, measure these ripples, feed it back in with a computer back into the mirror, and adjust the shape of that mirror maybe 1,000 times a second. If you can do that using the light from either a star or in a second we'll see from a laser, then the science light, the light you're interested in, can then go onto your high-resolution camera, and you can actually get a much higher resolution that's not distorted by the Earth's atmosphere. This is an incredibly powerful technique, and it's what's needed to get the sharpest images from the Earth. But you need a good reference star so you know what flat looks like, because you've got to compare it against something. And you can use a natural star, but there's not enough bright natural stars to do that. So the answer is to make your own star in the sky using a laser, which is coming back to lasers. So on the right here, you can see lasers shooting up into the night sky. At about 80 to 100 kilometers altitude, so well above the atmosphere, there's a layer of sodium that comes from meteorites. So if you shine a yellow laser on that, the sodium atoms absorb the yellow light and then they fluoresce back. And you detect the fluorescence light coming back from the sodium, and you know that's your reference. And if you do that, you can see on the left-hand side the difference that turning the system on makes. So without it, it's all blurry. Turn it on, it becomes sharp, and that's how you can analyze, for example, the motion of stars around the black hole in the center of the Milky Way galaxy. And it's how we know that there is a black hole there, and we know the mass of that black hole. So this is an incredibly important technique. So when we leave this lecture theatre, we can go outside and we have a green, not a yellow, laser guide star shining up in the sky. This is directly under the control of Sydney Air Traffic Control, so they may have shut us down, but we have permission. They're supposed to be keeping all aircraft away. The Civil Aviation Safety Authority have issued a NOTAM, which means no planes. We're right under the flight path, so you can see it takes a lot to arrange this. Please don't shine your own laser into the sky. Enjoy the one we have in the sky tonight, and it should be quite spectacular because it's about a 10, 20 watt laser, so it should be quite bright. This is becoming increasingly important. On all major telescopes, you need to have one or more laser guide stars. And with that, I'd just like to end by saying lasers are incredibly powerful tools. You can use them for so many different things. I didn't touch on a great many of them. And I'd just like to end with a few thanks to Ben Johnson, who's doing the guide star, Judith Dawes, Helen Pass, Dave Spence, Kelly Sharpless and team who've been doing all of the organisation, and to Graham and the Australian Institute of Physics. So thank you very much, and we've got no time for questions, but I'm happy to take them. Thank you. So I'm very happy to take questions if anyone has questions. Again, let's turn it on.
Hello. Thank you very much, David. When we think of it, that the laser first came about in 1960, so about 60 years later, all these applications of lasers, I like to think what sort of other applications in the next 50 years or so, what it's going to be like. I know in the news reports, even battleships and things are using lasers for various reasons. So thank you very much for that. So questions from the audience?
Everyone here?
Okay. I'll pass you.
Okay. So my question is about how lasers look to human eyes. When we had the green laser running exposed through the rig that you'd set up there, when we were talking about optic fiber cables, it looked like it had been segmented into a bunch of different tiny lines, and if you moved your eyes, the segments would move too.
Yes. So I assume you're not referring to the sticky tape holding it down, but you're referring to what's called laser speckle. So laser speckle is we got some feedback from the microphone. Laser speckle is a complicated phenomenon. It's like the fiber operating a little bit like a random hologram, but it shows you that the laser is coherent. The waves of light coming from each little piece of the fiber randomly interfere with each other, like I had that circle interference pattern on the screen, and that produces this speckly pattern. It's a very characteristic of lasers. You won't see it with any other light source. So a very good question.
Other questions?
One up the back. If you want to shout out, I'll repeat the question.
How loud's your voice, David?
Perfect. How do laser ranging retroreflectors work? Yes, so we have those on the moon. So just like you have a reflector on the back of your bicycle, which are designed with it's called corner cube reflector, and it's designed like if you throw a ball into the corner of the room and throw it fast enough, it should bounce back in the direction it came in. So that's just geometry. So if you shine a light on anything like that, you get quite a lot reflected back. So those have been left on the moon, and it doesn't matter what the rotation of the moon or the position is, they send the light back to us. So what you do is you send a pulse of light to the moon, and then you detect what comes back with a telescope and a very sensitive detector, and you time how long it takes for the pulse of light to go from here to the moon and back again, or wherever you've put the reflector. And if you know the speed of light and the time, you can work out the distance. So this is how we can measure the distance to the moon to a precision of a few centimetres. That's how we know that the moon is getting steadily further and further away from us by a few centimetres per year.
Thank you. Other questions? Down the front here.
There's one here and one here.
Excellent lecture. Thank you so much.
You're welcome.
I just want to ask about the project that is going to be launch a probe that's going to Alpha Centauri, and they're going to use laser. Can you just tell us how they're going to use laser, and then what is the technology that is behind that?
That's a very good question, and this is a very crazy project, but it's really exciting. So this is to launch a spacecraft that weighs a gram or two, and we launch many of them. And the spacecraft is accelerated by the pressure of light. So light actually has momentum, and if you reflect light off something, it gives a little bit of force. We can actually use that force in the laboratory to make what's called optical tweezers that can grab little particles and move them around. But to get a spacecraft that could be tiny with maybe a metre diameter, what we call a light sail, it's a few atoms thick and reflects light without melting. We don't know how to do that yet. If you shine an incredibly powerful laser at that, maybe you can get it to accelerate at something like 20 G for, I forget how long, there's a few minutes, until it gets up to about 20% of the speed of light, so you don't have to wait thousands of years for it to get there, maybe only a few decades. But to do that, you need insanely powerful lasers. In fact, you need a whole array of lasers, about a square kilometre of area of laser beam at incredible power to do that. So at the moment, I'm not sure what the numbers are, but you'd probably need almost the entire power output of the Earth to do that. So these things people are looking at them quite seriously to crunch the numbers to see whether this might be possible. And can it be done in our lifetimes to get something launched? There's an enormous number of technical hurdles, but it is one of the few established techniques or theoretical techniques that lets you accelerate something without using rockets. Because to use a rocket to get to another star, even our closest star, is pretty impractical because you've got to carry all that mass and energy with you. The idea is to not carry that, just send the momentum and the energy through a laser beam. But those laser beams have to be crazy large. The original proposal by Robert L. Forward, written in a science fiction novel, had a lens out where Jupiter is that was about 50 kilometres in diameter to focus the laser beam onto the spacecraft. This is the kind of thinking you need to do, but there's no other game in town at the moment if you want to physically send something there.
I'm sure if they discovered life on the Alpha Centauri system, they would fast-track the project.
I don't know that anyone's got deep enough product pockets to do that, though, at this point.
Any other questions?
There's a couple down the front here, but I guess while you're up there.
I saw that for, you said that to control the distortion of the atmosphere, we launch lasers, or yellow lasers, up to the sky. Is the distortion constant at the atmosphere, or is it different for each section?
That's a very good question. No, what happens is the atmosphere tends to be moving, so you get this moving distortion. Different layers of the atmosphere can distort in different ways. So a very complex system may have a whole series of mirrors correcting for different layers of the atmosphere. And so there's also, if you've got a very big telescope, the distortion is different in different parts of that telescope aperture, so maybe you need a whole sequence of laser beams, like that last picture I showed you where these very large telescope systems are now looking at having maybe 8 or a dozen laser guide stars. I think we had a couple of questions down the front. I can repeat the question if you want to tell me.
Okay. Yeah, thanks, David. Early in your presentation, you were describing energy levels of electrons and so on. You mentioned thanks. Early in your presentation, you mentioned energy levels and excited electrons and so on. I understand how some of that works, but you also said that in order to maintain a continuous laser, you need to have some kind of spontaneous emission to get rid of excess energy from the lower levels, or the sort of intermediate level, as I think you described it. How much energy do you need to do that? How much light do you lose? And where do you put the excess spontaneous emission? Where does that go?
Yep.
And if you have a really high-powered laser,
yes.
do you have a problem with all the spontaneous emission coming out of it?
Very pertinent questions, yes, yes, yes. So you dump heat into the material. So sometimes it is a spontaneous emission process, sometimes you lose energy through more complex process, including involving phonons, which is thermal excitations. So that little crystal of sapphire I held up earlier, we have to water cool this to get the waste energy out. Very, very high power lasers, we're looking at things, can you use something like diamond, which has got a better thermal conductivity than copper. The other element is the amount of energy you dump depends very much on the energy level structure and what fraction comes out as light versus gets lost. So the relative position of those energy levels is very important for high power laser systems. And some of them, we call that the quantum efficiency. For one photon going in of a certain energy, what is the energy of the photon that goes out that we want, and what's the bit left over? And some systems can have very high efficiency, 90+%, and some systems are very inefficient and dump a huge amount of heat. So yeah, that's a really important question. It's a lot of what laser engineering and laser physics is about, is handling exactly that issue. Thank you.
Okay, probably getting a bit late. Maybe one last question. Are you able to shout it out from there, or?
There's one just like that. Yes, so as you go to longer and longer wavelengths, we get into the very first thing that came before lasers, which was masers in the microwave part of the spectrum. And you even get natural masers in molecular clouds in, around stars in interstellar space. So that's at one end as masers. Then if you go to longer, you can just directly drive things with a radio. So you don't need to use the laser type process. You just directly drive the electromagnetic wave you want. At the short end, to make a gamma ray laser, as far as we know, the only way to do that is what I alluded to, is using a nuclear explosion. That produces enough energy to potentially make gamma rays. So part of the US Star Wars program was to have a nuclear explosion in space surrounded by a whole lot of rods that would, as they're blasting, would produce gamma ray lasers. Kind of crazy stuff. So not in the laboratory is the answer.
David, I might just ask actually the very last question. All your lasers we've seen so far have been man-made, but I believe some lasers have been seen up in nebulas and things like that, been created by nature. Did you want to comment on that?
Yeah, so that tends to be more masers in the microwave part of the spectrum, and so indeed that's the energetics up there are such that over these vast distances I think it's the commonest one is in hydroxyl molecules, OH. I don't know the full physics of exactly what the energy mechanisms are that's pumping, but there's a lot of stuff happening there in terms of hard radiation, radiation from stellar activity causing excitation, and you get natural. There's no mirrors in space, but if you have a long enough system with gain, a little bit of spontaneous emission gets amplified until you get something that looks like a laser beam coming out, pointing towards the Earth, and that's what's detected using radio telescopes and microwave telescopes. So that's the natural occurring lasers. I'm struggling to remember if there's ever been a visible laser naturally occurring. I don't think there has. I think the energetics, there's too much you've got to do to get it to work for it to occur in nature.
Thank you. Professor David Coutts, if we can thank him once again. Thank you.
Thank you.
Now, just a reminder, outside there's a demo on a laser guide star of what we saw, David spoke earlier. So it's outside in the courtyard. So you have to go past it before you see it. Okay, thanks very much everyone, and thanks for coming along.